Hello dear engineers, this study presents an automatic infrared-based volume and mass estimation system for agricultural products alongside with major geometrical properties. The goals are decreasing human error and save more time using color and depth images, and system works in irregular and non-symmetrical shaped fruits in different distance from sensor. Also extracting 10 color and depth image features and fast response in real-time calculation. As an introduction, we have to say better healthcare leads to more population. More population means more source of food. As demand increases, it lifts up the supply. Modern tools to plant, harvest, quality evaluation, and packaging are required. In quality evaluation part, product grading plays an important role in quality management. Volume and mass estimation are part of product grading process. Traditional volume estimation method and mass estimation method are called water displacement for volume and digital balance for mass. Water displacement method is so time consuming and damages the products, doesn't calculate the exact amount of volume in agricultural products in different shapes. Digital balance is time consuming and affects the freshness of the product. To fix could use heavy machinery, but it is costly and require more space. Here we can see water displacement for volume and the digital balance for mass, which are traditional methods in the left and right. Computer vision techniques had impact in agricultural product processes. One of the best impacts in grading process like volume and mass estimation. There are decent color image-based techniques in order to do that, but with some issues. Proposed method lifts up the existing methods to level higher and improve in precision, different distance, and also in pure darkness aspects. ICCKE is one of the most famous depth sensors. It is low cost and available out there. Employs night vision technology. Works based on infrared particles in decent quality and resolution. It's proper for both research purposes and applications, and it is our main tools here. Here we can see different parts of the ICCKE sensor version 2. Here we are seeing a plot or a figure for an eggplant in color and depth images, and it is a depth structure showing an intensity channel of an eggplant vegetable. The smaller value means closer distance to the sensor and vice versa. It is a standard color image of the same eggplant. Depth images are 2.5 dimensional images. It is possible to convert 2.5 dimensional image to a 3-dimensional image by a simple processing. Now, in order to prior related research, we have three main studies of Jana in 2020, which is Jana and partners in 2020, which they use automatic volume and mass estimation of fruit and vegetables. They use the ordinary smartphone color cameras. System works for irregular and non-axisymmetric products in a specific distance from sensor. Potato, tomato, and citrus products with 77 samples in total are used. Their system did not support pure darkness situation and also in different distance. Another valuable work is belong to Vivek and partners in 2015. Which they use volume, they actually perform volume and mass of axis symmetric fruits using color sensors in a single view. They estimate that. They extract the boundary contours. They categorize the fruit into circular and elliptical shapes. Volume is calculated based on a specific fruit in each experiment. Mass is calculated based on relationship between mass and volume. 4 types of citruses in validation section is used in total of 120 samples. Their system does not support irregular and non-symmetrical shaped products. Another mentionable and valuable research belongs to Musavi and Prasad in 2019. They employed depth sensors, which was Kinect, for different products distance of 0.8, 1 meter and 1.3 meter from sensor. System starts with pre-processing steps, estimating the weight using average weight of the experimental product and its distance from sensor plus a constant. Finally, normalization of the final value into gram. 150 samples of sweet lemon, sweet pepper, and tomato are used for validation, but just estimating the food weight. In our method, a robust infrared-based volume and mass estimation system for fruit and vegetables is presented. We fixed some issues in available new and traditional methods, works on irregular and non-symmetrical shaped fruits in different distances from sensor, and fast response in real-time calculation. So we have a pre-processing step which starts with a median filter followed by a sharp mask filter on both images. It helps for smoothing from inside and sharpening from the outside. Then canny edge detection filter applies on both images. Then filling unnecessary holes using closing morphology operation. Active contour segmentation, extracting region boundaries, and background extraction steps are in pre-processing stage. So we are extracting 10 2D and 3D features from color and depth data. From color data, length, width, diameter, and perimeter features are extracted. From depth data, thickness or height, surface area, volume, convex volume, solidity, and mass are extracted. Here we can see a sample of dataset, which some steps of pre-processing on the color sample for proposed dataset on a 2D or color data is visible. Here some steps of pre-processing on one of the depth samples from proposed dataset is visible. So for feature extraction from 2D data, we have length and width, which are length and width features are axis pixel count based. 2D diameter, fruits are non-symmetrical, and carrot is not circular among other circular ones. So diameter has different meaning here. Diameter calculates two biggest axis pixel value which are more than 0. Finally, a straight line in centimeter determines the diameter value here. For 2D perimeter is the distance around the boundary of region around the 2D shape. It computes the perimeter by calculating the distance between each adjoining pair of pixels around the border of the region. Finally, we can see these 4 features are extracted from one of the samples of the dataset, which is garlic. So for 3D features, we have thickness or height. Depth sensor calculates the distance between the sensor and the products. This might some bump be on the surface of the sample. Thickness is the highest gray level achieved from top surface of the sample in depth data. So data is recording from 2 sides, and each side gives a slightly different value of thickness. The largest amount of 2 will be selected. For 3D surface area, due to the regular shape, it is not possible to use common equation of 3D surface area. We will subdivide it into some familiar shape and calculate the area of the familiar shape. Sum those area calculation to get the area of the regular shape they make up. Yes, we use 3D model shape in this research, which is based on mesh, and the mesh model is made of triangular faces, so we have to use triangular calculations here as below. Other feature for depth data is 3D convex volume or solidity. It gives a set of points in plane. The convex hull of the set is the smallest convex polygon that contains all points of it. Now the convex volume is the volume of the convex hull, which its mesh structure is based on triangular calculation. A voxel is a raster graphic on a 3D grid with the values of length, width, and depth. Proportion of the voxel in the convex hull that are also in the region returned as a scalar, which is computed as volume divided by convex volume, is called solidity. which is our other 3D feature. 3D volume. 3D models are based on mesh model, which basically based on triangular shapes. In the surface area, it was sum of 2D triangular area values on the model. But 2D shapes have no volume, so the triangular prism makes our final 3D mesh model. Calculating sum of the 3D triangular prism, which makes the final model, 3D volume of the fruit will be calculated as below. So we have 3D mass. There is a relation between volume, mass, and density. Having two of them, another one is calculable. Each matter has its unique density, which agricultural products are not exception. Garlic has average density of 0.74 gram per cube centimeter. Carrot's density is 1.40 gram per cube centimeter. Potato has density of 0.63 gram per cube centimeter, and quince density is 0.91 gram per cube centimeter. The relation between density, volume, and mass is as below, and the 3D features is so the final 3D feature is as below, which in which T, S, V, C, S, and M are thickness, height, surface area, volume, convex volume, solidity, and mass respectively. So the final feature vector would be as the sum of all of them, 2D and 3D. Here we can see appliance of 3D features on a sample from the depth sample from the dataset and the value achieved from the process. In order to validation, we made a dataset which is total of 60 samples in different shapes. They are axisymmetric, non-axisymmetric, regular shaped, and non-regular shape. Consisted of 20 potatoes, 50 garlics, 50 carrots, and 10 quinces. For lighting, we use EDC bulb 9-watt power light, and the sensor is Kinect version 2 sensor, is placed in different distance from the sensor, which is adjustable, and Windows 10 or 64-bit operating system alongside with MATLAB software. Here is the recording setup environment. As we can see, all the device, sensors, lighting, fruits, and softwares. Here are some samples which are recorded in the datasets in depth and color sample forms. For validation, we use two metrics of mean absolute error and mean absolute percentage error. Mean absolute error is the average over the test sample of the absolute difference between prediction and actual observation, where all individual differences have equal weights. But mean absolute percentage error is a statistical measure of how accurate a predict system is. Statistically, the average absolute percentage error for each time period minus actual value divided by actual values. So for some plots, we have linear regression, which linear regression attempts to model the relationship between two variables. One variable is considered to be explanatory variable, and other one is considered to be dependent variable. Here we can see comparison result for proposed volume estimation method versus water displacement method for garlic samples in millimeter at top, and at bottom we can see comparison result for proposed mass estimation method versus digital balance method for carrot samples in gram. Here we are watching comparison result for potato samples, which we have 20 potato samples as left, as we can see. Volume and mass, which is volume is 0.63 gram per cube centimeter. Density for potato and mass is in gram. Also we have runtime speed just for proposed method. As we can see, proposed method have better result than other traditional and modern methods. As we can see, the error value for proposed method is very smaller than others. The same volume and mass estimation results for garlic samples and runtime speed in comparison with traditional and modern methods can be seen here. Here we can see that proposed method has lower error actually. The same for 15 samples of carrot. Again, proposed method actually had perfect results and better than others with lower error values. And queen samples here are vivid. The results are satisfactory. Also MAE and MAPE for volume and mass, again for 4 products of potato, garlic, carrot, quince in comparison method for proposed and other methods are visible here. As we can see, proposed method has low amount of error. Here we can see linear regression for potato samples for proposed and butter displacement method for volume. These two variables, proposed method versus digital balance, which is mass for these two variables at the middle, and proposed method versus proposed method in volume and mass at the right. As a conclusion, we can say adding depth data to color data increases the final detection and recognition accuracy. Kinect sensor is a suitable tool in agricultural product grading. 3D features plus 2D features fixes some traditional and color-based method weaknesses. Single image based, our system is single image based and non-learning based, so it is so fast. Cheap price, it is so rational to replace it with digital system or traditional heavy machinery. No product damage and no high error in a big scales. Also, it is suggested to use more fruits and vegetables with the system, to use more than 2 angles on agricultural products, and also to use more sensors for simultaneous recording. Here we can see some references which are used in this research. And finally, thank you so much from all of you for your attention.